Good morning, everyone. Welcome to DSA class. In your previous class, I already discussed about what is DSA, what is data structure and algorithm. Data structure is a way to organize the data that we can use it efficiently in the basis of time and space. So today we learn the time complexity and space complexity. Now, okay. Today we begin an important and practical topic, time and space complexity. This is to concept help us measure how efficient our programs are in terms of speed and memory uses. Now, why should you care about this? Because no matter how correct your program is, if it runs too slowly or use too much memory, it might not be usable in real world scenario. Imagine, imagine imagine you write a sorting algorithm, but it takes 10 minutes to sort 1000 numbers. Okay, while someone else code does it in 2 seconds. 2 seconds. Which program do you think people will actually use? Obviously, the first one. The first one. This course will teach you how to measure measure how good or bad your program is, and write programs that run faster and solve new and complex programs and come up with smarter, optimized ways to solve problems. So, by the end, you will be able to evaluate the quality of your code in terms of how quickly and efficiently it performs. Now, before we dive deeper, let's understand a few basic terms that we will use. Algorithm. Algorithm. Algorithm is a step-by-step method or procedure for solving a problem. Think, think of like a cooking recipe. It tells you what to do, in what order, and when to stop. Yes. Now come to the program. Now come to the program. Program is a implementation of an algorithm in some programming language. We just write the algorithm and we do this program using any language, Python, Java, C++. Okay. Now come to the data structure. This is how we organize and store data in computer so we can access and modify it efficiently. Efficient in basis of in basis of time and space. Okay, now take one example. Just like how we organize clothes in a wardrobe. Shirt in one place, pant in another. We just arrange those data. Yes. So in case of data structure, when we organize the data using some basic operations like as array, linked list, stack, queue, tree, graph. Okay. Now come to the next. Basically, we know that algorithm is a set of instruction to do a program. So, for one program, it's maybe for one program, for one program, 1 minute. For one program, there is many algorithm present. There is many algorithm present. This is A1, this is A2, this is A3. We can solve this program using many algorithms. Okay, we can solve it. But which one is good? How we understand that which one is good? A good algorithm is not just about solving the problem correctly. It should also run quickly, use little memory as possible, less memory, need and less space need. Less memory need and less time it required. Okay, but many things affect how fast a program runs. For example, whether you are using a single core or multi-core processor, whether the system is 32-bit or 64-bit, and how fast data can be read from or written to memory. It's matter. The biggest factor, however, is the size of the input. If your input is small, even a slow algorithm will finish quickly. But what if your input is huge? When the line of code is huge, then efficiency becomes critical. Yes or not? That's why we need to measure performance in terms of how it behaves as input size increases. Yes, now come to the time complexity and space complexity. So, we measure the time through the time complexity and we measure the space through the space complexity. Time complexity. Time complexity means time complexity is the amount of time a program takes to run. We measure this by counting basic operations. not second, because time on a real clock can vary depending on the machine. Yes. And space complexity. Space complexity is the amount of memory or storage a program needs to compute its tasks. This is space complexity. Now for example, when you search for a contact in your phone may use an efficient search algorithm to quickly find the name. If it searches each name one by one, it would take too long. And if it loaded all contacts picture and details into memory first, it would use a lot of space. Yes or not? So good programs must balance both time and space. Yes. Now come to the point. Basically we measure the algorithm two way. One is priority and another one is posterior. In posterior means we measure the time after execution. Okay. And priority means we measure the time before execution. So in a posterior, we got the data is exact because it got after the execution. So now if you use C and C++, you can use this clock function. You can use this clock functions from time.h header file. To measure how long a piece of code takes to learn. A small example, clock start and finish. After that you got start clock. This code gives you the time taken in the second to sort the array. Now it gives, I just taking it 0.44 second. Okay, it got the result 0.4 second. But it only works for the current environment. The same program might take a different amount of time on a different machine. It takes 0.4 second, but now I change the hardware. Now I change the software. Then maybe this time is vary. If it is 32-bit machine, Now I change to 64 bit, or I just change the processor. If it is i3, now I change to i7. Obviously this time will be decrease. Now this is take 0.1 second. Yes or not? So this posterior time measurement depends on particular, this is dependent on particular software and hardware. Yes. So it's changeable. So we are not taking this for the time complexity measurement. We take this one. Priority before execution. So before execution we measure the time. Means this is a approximate value. It's give the approximate value. It gives the approximate value. It is independent from hardware and software. If I change the hardware and software, then maybe it not change the value change the output, because it's assume something. We assume the time complexity from the program. Okay, so we take the priority time complexity. Okay, now come to the next. So this is the limitations. I just said that in a posterior it is necessary to implement and test the algorithm in order to determine its running time. In order to compare two and more algorithms, the same hardware and software environment should be used in case of posterior. Okay. Now then, how to analyze time complexity? How to assume, how to take the approximate value. Now this is a one program. We just passing two variable int a and b, and we just take the value a plus b. Okay, we return the summations value. Then what is the time complexity? Time complexity for this line, there is a, we need 1 unit of time. For this line we take 1 unit of time. So total 1 plus 1, 2 unit of time. This is a constant time we need. This code performs 1 additions and 1 return. So we say it takes 2 units of time, since this time does not depend on the size of the input. Size of the input, it not depends. It is a constant time. So the time complexity is order of 1. Okay. Now take another example. Here we just pass one array and one variable n, and we also initialize sum is equal to 0. There is a one line and this is the second line, and there is a one iteration is performed, one loop is present, and in the next line sum is equal to sum plus 1. Means this is a number 1 line, this is 1, this is 2, this is 3, this is 4, and this is 5. Okay, there is a 5 line. So in this line, this is takes 1 unit time, this is 1 unit time, and this for loop goes to n times, n, and this is I plus plus, so this for loop goes to n plus 1 times, and within a loop this is present, that's why it also execute n times, and this is 1 times. Okay, so total time complexity needed 1 plus 1 plus n plus 1 plus n plus 1. Okay, so this loop runs n times, so as the input size increases, the time increase proportionally. Yes or not? If the input size increase, then obviously the time also be increased proportionally. We call this linear time complexity. That's why the time complexity is order of n. Okay. Now take our one example, counting how many students are present in class. If you check one by one, time increases with the number of students. Yes or not? Okay. Now come to the next point. So there is a 5 important guidelines to finding the time complexity in a code. One is loops. Time depends on how many times the loops run. Means it may be order of n, it's maybe order of n square, n cube, etc. Means its times depends on how many times the loop runs. Next one is nested loop. We already know that what is nested loop. So when one loops under the another loop, then this is a nested loop. So multiply the complexities. One loop inside another. So this is if one loops placed another loops, then this is order of n into n is order of n square. Okay. Next one is consecutive statements. Add their time complexities. Consecutive statement one by one adjust add their complexities. Okay. Next one is if else. Take the complexity of the branch that takes more time. In a if else statement, which branch is takes maximum time, we just when we calculate the time complexity, then we take only which one is higher. Okay. Next one is logarithm statement. In case of when we want to calculate the time complexity in a logarithm statement, this is often appear in divide and conquer strategies like binary search. This is order of log n. Order of log n. Okay. Now come to the asymptotic notation. So basically here we just write order of n square, order of log n. So what is this O? Basically when we learn the asymptotic notations is basically used to describe the performance of an algorithm as the input size becomes very large. When the input size becomes very large, then asymptotic notations come. we represent symbolically represent the time complexity. So there is basically 5 types of time complexities are there. One is big O, another one is big omega, big theta, little o, and little omega. Okay, so big O. Big O basically used in worst case, or you can say this is used for upper limit. This is describe the upper limit. Okay, next one is big. This is big O. This is big O. Next one is big omega. Big omega, we just write in this way. Okay. Big omega is basically used for best case. Best case or lower limit, or it describe lower limit. Okay. Next one is big theta. Big theta. It is used for average case. It is used for average case. Okay. And next one is little o and little omega. It is little o and little omega basically used for more precious but rarely used in practice. It is tight upper bound, tight upper and lower bound, tight upper and lower bound. Okay, basically we use we use those 3 types: big O, big omega, and big theta. Okay, now come to the asymptotic notations. Now come to the big O notation. Big O notations gives us upper bound. It tells us the maximum time an algorithm might take. Okay. Given there is a 2 function, one is fn, another one is gn. We say that fn is order of gn if there are positive constants c and n0 such that fn greater than equal to c into gn, where n greater than equal to n0. Okay, so now take one example. if an algorithm has time complexity order of n square, you give it 1000 inputs. It might take roughly 1 lakh steps in the worst case. So this is useful because we always want to prepare for the slowest possible solution. Here you just take, there is a one example 2n plus n. There is a fn, this fn function is already given, okay, and we have to calculate this gn. So there is a fn function is 2n plus 10. This is, now in this formula you just put this one, fn 2n plus 1 greater than equal to less than equal to c dot n. Here we take n, this n, but for n, which value of n it gives the true result. If you check it, then when n value is greater than equal to 10, just put it n is equal to 1, then 2 plus 10, how much? 12. 12 is less than 1. Okay, it's a false. Now when we take greater than n value is greater than 10, then it satisfies these equations. So n0 value is 10. This n0, after n0, you just check always gn value greater than fn value. Okay. Now there is a one example. If you take one example, now I just take one example. F of n is equal to 2n square plus n. Okay. Now you have to calculate that f of n is equal to order of what? Order of what? Now calculate it. Just put it into formula. Just put it into formula. 2n square plus n less than equal to c into g of n square. Why I take n square? Because here the n square and n present, which one is greater? This n square. That's why we take this n square. But you have to calculate this c value. Now put it when c is equal to 3. Then we can see 2 n square plus n less than equal to 3n square. Okay, so you just subtract it and we got n less than equal to n square. Now divide it and we got 1 less than equal to n. So can I write n greater than equal to 1? So for all the inputs n greater than equal to 1, this condition always true hold. Yes. So now this is a big O. So it's clear that how we use the big O notations. Basically we use the big O notation most because this is says about the upper limit. Okay, now come to the, and those are the big O example, more example. You just see 7n minus 2, where c greater than 0, n0 greater than equal to 1. Just see the see this picture here. After the certain point, you check always gn always greater than fn. You have to find out this certain point. Okay, now next one is growth rate, big O and growth rate. If you check when comparing two algorithms, always choose the one with the lower growth rate. For example, on is better than on square. Yes, O log n is better than on. Why? Because as the input grows, the one with the lower growth rate will remain faster. The big O notations give the upper bound on the growth rate function. The statement fn is order of gn means that the growth rate of the fn is no more than growth rate g of n. Okay, take example on is better than on square. There is a one series is that you can check that which one is better and which one is lower. Okay, 1 minute. Actually, basically order of constant. Can I create another one? 1 minute, just 1 minute. Okay, press one. If you check this one, just remember these things. Remember these things. Order of constant is less than order of log n, and this is less than order of log n. This is order of n to the power half, and also it's less than of order of n. It less than order of n log n. Order of n square order of n cube order of n to the power k order of 2 to the power n order of n to the power n order of 2 to the power 2n. Okay, so this is the comparison of various time complexities. This is the higher time complexities. After this, order of n to the power n, next order of 2 to the power n, next order of n to the power k. You just remind those sequence. Okay, now come back to your PPT. Now Next one is big omega notation. Just first see the pictures. Here in this x-axis we plot the n and the y-axis we plot the t. N is the size of input and t is the time. How much time is required, and n is equal to the size of input. Now see the picture. Here this is a function which is given and we have to check this gn function. Okay, big omega gives us the lower bound, the best case. The best case example in binary search, if the item is found in the first guess, it takes only one comparison. That's the best case, omega of 1. But we don't rely on this too much because best case is not guaranteed. We just got at the first guess, but always it will be happen, it's not possible, no? That's why this best case is not guarantee, not give the guarantee. But you check this c of gn less than equal to f of n. Just see the picture. F of n always greater than c of gn, and there is a certain amount of time. Later the certain amount of time you have to find this n0. Okay. Now you can check the example also. Now check the same example. If you take two, okay, if you take 2 to n square plus n, okay, 2n square plus n. Now you have to find out. Now put the formula. We already know that f of, we already sorry, we already know that f of n is equal to big omega of gn, 2n square plus n, 2n square plus n is equal to c into g of n. Okay, g of n. Now take it. We just write 2n square plus n c into n square. Okay. Now c value is equal to 2. Now take 2n square plus n greater than equal to 2n square. Then can I write n greater than equal to 0? So for n greater than equal to 0, it always true this equation. So basically big omega says the best case used for best case, and it's provide the lower bound. Okay. Now come to the PPT. Next one is, so you can say that big O says your algorithm is at least this good, and omega says your algorithm is at least this bad. Next come to the theta. Theta notation. See, See this picture. Theta used in a average case. Theta gives us a tight bound. It means the function always grows at that rate in the best, odds and average case. For example, some simple sorting algorithm like insertion sort take order of n square in average and odds case. Now this is a fn is already given, and this is a upper bound and this is a lower bound. In average purpose we use the theta complexity. Okay, so now take one example. This is a one textbooks and you want to find any word which one is present at the first case or first page, then this is a best case when you got at the last page, then this is a worst case when you got at the average, then this is a average case. Okay, how we represent it, it's clear that we just write this fn and here this is upper bound, this is a lower bound. Okay, now small o notations and small o notations, there is a only one change, not equal to, it's only this less than. Okay, and you also can describe this 1 minute. Now small o notations, small o notations, if n is equal to order of gn. Okay, easy meaning, it is a easy meaning says that if n is much slower than gn when it becomes very large. If n if n is much slower than g of n when n becomes very large, n becomes very large. Very large. This means as n goes to infinity, okay, then gn becomes very large. So n goes to infinity, then we can say f of n divided by g of n goes to 0, goes to 0. Yes, for example, now let's take one example. F of n is equal to n, okay, and g of n is equal to n square. Now divide them. Now divide them. F n divided by g of n. Now this is n by n square. Now this is 1 by n. As n becomes very big, so 1 by n becomes very small. It goes to 0. It goes to 0. So n is order of n square. So we can say this is the time complexity of order of n square. Because of n square, it goes to 0. Clear or not? Now come to the small omega notation. Small omega. F of n is equal to omega of gn. Okay, omega of gn. Easy meaning that Fn is much bigger than Gn when n becomes very large. This means n goes to infinity. F of n divided by g of n goes to infinity. Fn is much bigger than Gn when n becomes very large. For example, now take one example. F of n is equal to n square. Then g of n is equal to n. Now divide them. F of n divided by g of n is equal to n square by n. Then we got n. So as n becomes very big, n goes to infinity. When n becomes very big, then n goes to infinity. Yes or not? So we can say this is time complexity is omega of n. Because of n, this n goes to infinity. So f of n is equal to small order of gn, meaning is that fn is much smaller than gn, and f of omega of gn means fn is much bigger than gn. We can say. Okay. Now you can take one example also for the visual representation. Okay, now goes to the PPT. Small o notations over. Now small omega over. Now come to the space complexity. What is the meaning of space complexity? Space complexity. Let's now step to focus the space complexity. It measures how much memory an algorithm needs to run. This includes space of instruction, space of variables and data, and stack space. Okay, or function call, especially in recursion. This is a space complexity. How much space is required to run the program? Now come to the one by one instruction space, data space, environment stack space. Instruction space. Instruction space is the memory used to store the compiled versions of the program. For example, there is an expression a plus b plus c into d. The compiler may rearrange this into a more optimized form is internally c into d plus a plus b and store it efficiently. So this is a instruction space. Here this a plus b plus c into d, we just optimize it c into d plus a plus b. Okay. Now next one is data space. Data space include two components. One is space of constant and simply variables, and second one is memory for dynamic object like arrays, linked lists, etc. For example, if you declare an array of 1000 integer, the array will take up much more data space. Yes. So it is important to manage this space efficiently, especially when working with large dataset. Now there is a one example. There is a one example. This is a factorial of a number programming. Now we just check how the space is utilized. How the space is utilized. Now we already know how to write the factorial program. First you just write as include st dot h. After that you write int factorial, or you just write take the name fact. This is a user defined, you can take anything. Now you just pass one argument int n, and after that you taking the second bracket, and there is a one conditions if n n equal to 0, and we're just taking this also, or n equal to 1. In a C language, for when we write the equal sign, then you have to write this equal sign. And next one is return 1. If the value of n is 0 and 1, then factorial gives the result is 1. Else you just write return n into fact of n minus 1. Here n minus 1. Here the recursions we call the function itself. Then this is called the recursion. Now you just write int main int num. I just taking another variable which name is num, and printf enter the number, scanf percentage d ampersand num. Printf factorial. Okay, printf the output we just print num. We print num and factorial fact num. Okay, and next return 0. Now you already know Thus this is the one program to write to this is a program for calculate the factorial of a number. We just write this code in a C language. Okay. Here we already know that we use this header file. Why we header file? This is a preprocessor directives. Preprocessor directives to says the preprocessor to include this header file. This header file, standard input output header file, contains these printf and scanf functions. That's why here we use this header file, and after that we call one function which name is fact, and we pass the one variable which is n, and there is a one conditions. We know that when n value is 0, then factorial always be 1, and when n value is 1, then factorial also be 1, and after that it's called itself. That's why there is a recursive call present. This is called the recursions. When one function is called itself, then this is called recursion. And in this main functions, compiler goes to the first main function. In the main functions we take another variable, this name is num, and enter the number it's showing in the output screen, and in a scanf functions we taking the number from the user. We taking this is integer value. That's why the format specifier is %d. We already know that. So so we check here that what is space complexity, how it takes the space. Okay, we check it. Now when you call the factorial n, when you call this fact function, when you call this fact function, then we goes to here, yes or not? Okay, so if you check here, this is a recursion. So 1 minute. Now this is a, now I take the n value is 4. Okay, now we take it, n value is 4. Okay, so first is a factorial num, so 4, and it is 4 and fact 4 here. Then this is come to here and check these conditions. Now is come to the else part, and it's check n into fact of n minus 1, n 4 into fact of 3, fact of 3. Now it goes to check the same things. Now it is 3 into fact 2, fact 2. Now this is becomes 2 into fact 1, fact 1. Now it becomes 1 into fact 0, fact 0. When it is 0, then it is written 1, means 1 into 1, it's 1. Now next one is 2 into 1, it's 2. Now this is 3 into 2, it's become 6. Then 4 into 6, it becomes 24. Then it gives result the 24. So here each call waits the result to the next call. First it gives the result this one, then this one, then this one, then this one. So each call waits for the result of the next call. This creates call stack. Yes. So what is the space complexity? Because of each function call use stack memory. For recursive function, each recursive call adds one frame to the stack, and total depth is n calls. Total depth is n calls. N calls. So space complexity is order of n. So space complexity is order of n. And you also can check the time complexity. Here the calls is n times, so time complexity also be order of n. Okay. If you check this recursive function, this factorial function, if you use in a iterative versions, then you check there is a no recursion, so no stack build up. So in case of, you just see the time complexity is order of 1. You write the iterative write this function in a iterative versions, and you can check the space complexity is order of 1, because here no stack is present, so the time complexity is order of 1. Okay, so come to the end. So to summarize today's lecture, one is time complexity. What is time complexity? Basically, time complexity help us understand how fast a program runs. Next one is space complexity. Space complexity tells us how much memory it needs. We use asymptotic notations like big O, big omega, theta, small o, small omega. How performance changes with input size, we also describe it. So, understanding this as concept is essential for your writing better, scalable, and more efficient software. In the next class we will analyze real algorithms using this as principles. Okay, thank you everyone.